up to a day late, meaning up to 9 p.m. on a Saturday, on the Saturday following, you lose 10%.
Sir.
Yes.
Question on that note right there, sir. So up to a day late at 2100 hours on Saturday. 2100 hours on Friday is a deadline. What if between 2100 hours on Friday and 2100 hours on Saturday, we do a submission? Not saying it will be a deliberate, but unforeseen circumstances allowed you not to submit it during the stipulated time, but within this time frame. Will there be penalties as the same?
All right. Can I say, Mr. Cortez, Mr. Wilby, that this is actually a lowering of the penalties that were applicable for past groups. The 10% usually apply once it is after 9 p.m. Once it came in on Saturday, you would have lost 20%. So this is actually a relaxation because we are now applying it across the faculty. So in other words, if it comes in at 2101, you're going to lose 10%.
On Friday, sir? On
Friday, yes. If it comes in on 1 minute after 9 on Friday, it's 10%.
Then, sir, this should be changed on Friday, sir.
Pardon me?
The 10 here at point 1, it should be 2101 Friday, not Saturday.
No, up to a day late. That's what we're saying. So up to a day late. Remember, the deadline is Friday at 9. So until Saturday at 9, it will be 10%. So from a minute after 9, I mean, as I said, it has been changed because we are going right across the school with this. But in previous years, you would have lost 10% between 9:01 and midnight. And then after midnight, you would lose 20. But that is now, we have now revised that. All right. So these are the penalties. Quite frankly, students, you have 2 weeks to do the labs. You're doing the labs, you'll be doing the labs in groups of 2. What I prefer to be focusing on is the fact that you are submitting your labs from Thursday and not even consider these penalties. That's what I want from level 4 students. All right? So let us not be even too concerned about these penalties. If you are hurrying to get in the lab at 9 p.m. on Friday, what it will tell me is that you have not, or you would not have been able to spend the quality time to not only complete the lab, but to review it. Because it's important that you review, think about what you're presenting. Yes? I usually tell students that to know whether or not you have done a good report, ask a non-engineer, a non-technical person to read your report. And if they understand what you have presented, then it means that you have done a good report. That's my recommendation. But of course, you won't have that luxury if you are hurrying to submit at 9 p.m. on Friday. As a mark scheme, at the top, we have an oral assessment. So yes, you have completed the lab. You have, submitted the document, but we want to make sure that you understand what you're doing, that, although you're working in a group, that both persons are able to use the software package. Because one of the objectives on your on your syllabus is that persons would know this software package, at least one software package. This is the one that we have chosen. So after completing a couple labs, we will do an oral exam, which will test your ability to use the program, your ability to execute certain activities using the program. So nobody will be able to hide behind anybody. Yes, you know, we allow the group work, but that is just for, you know, helping you to work with other people towards a common outcome. But we still will ensure that everyone does their fair share as far as the lab is concerned. Take careful note of item 2. All right, yes, we do assess persons for the use of English. This is a report. And so the tense that you use is important. And for the English students among us, you may think that this would be a given, but you'll be surprised. I've had labs written to me in the present tense. And just your general use of language. And I'm saying it is therefore even more important that having written the report, you're going to spend some time to review it to make sure that it is well done. Okay, so I come now to theory.
Good evening, Doctor. I have 1 minute.
All right, tell you what, note your questions so to get to the end. We'll go through them, all right?
No problem.
Just note your questions. All right. For your theory, best way I've found to explain what a theory is that it is simply the basis on which you're going to carry out this experiment. So you want to look on the principles that govern what you're going to do. Yes? And it is important, students. I cannot overemphasize this. It is important that you understand the theory that you present. So don't just go to a Weedy or a Duncan, Glover and Duncan, and simply write what they have in those texts. Or go on this website and just grab some stuff and throw in it. No. Spend time reviewing what they have said. Look at you first need to look at the objectives that are in the lab. What is it that I am being asked to assess? What is it that I'm being asked to research? Look at those objectives, and then you're going to spend some time identifying the principles or outlining the principles on which I am going to test these objectives. That is what, that is what your theory is about. So, you know, as I said, the marks there reflect what we are expecting. When it comes to results and calculation, what are we giving a mark for? In a sense, every student at this level, you can, you know, plug in some or carry out some exercises. You see some numbers and you can write them down. What we'll be assessing here is how you present this data. So is it more efficient to present the data or the results in a tabular form? Or is it more efficient to use, you know, graphs? If you're putting it in a table, do you give me 5 different tables, or can you summarize the information in those 5 of those 5 tables in a single table. All right, so it's important that you're thinking about how best to communicate your results to your reader, which is of course myself and Mr. Sawyers. Yes. So it's not just about putting down the results; it's how you present them. There'll be some questions. We'll also assess you on these questions, and these questions primarily are, for use of a better word, lead questions, which will help you craft a good discussion. Yeah. But answering these questions do not equate to a discussion. Let me repeat. Answering these questions do not equate to a discussion. Your discussion, ladies and gentlemen, let me try and go slow with this one. Your discussion must be that you are discussing your results based on the theory that you have presented, which is why I said earlier, it is important that you understand the theory. So your classic Ohm's law, let's say you have presented Ohm's law in your theory. If you then came to your results and you saw where, you know, the current and voltage values that you have calculated resulted in a straight line, then when you come to your discussion, you're saying, well, based on the fact that the voltage and current values that I have plotted results in a straight line, that is showing direct proportionality, etc., etc. You with me? So spend time on your theory. It is 20%. Because if you understand the theory, then when you have your results, you can quickly discuss them. And then finally, for your conclusion, and surprisingly, many students give back this 5% to me, and I can't understand why. But your 5% for your conclusion is based on you concluding on the objectives that were set. So you need to look back at the objectives. Yes, look back at the aim. What were you doing? What were you seeking to test for this in this exercise? And make a concluding statement. I do not want to see any two paragraphs for a conclusion. Once I see that my reading, you know, start flying, your conclusions must be simple statements where you're making a concluding statement based on the objectives in light of the discussion that you have just presented. All right? Okay. So let me pause there, because I know I've said a mouthful where this is concerned, and I saw that Mr. Hope had come in earlier, so let me give him an opportunity to ask his question. Mr. Hope. You change your mind?
Can you hear me, sir? Can you hear me, sir?
Go ahead.
Yes, I was asking you, in terms of how often are we going to do a lab, every week or every other week?
I hope you came in late?
Yes, sir. Well, I came in.
All right, if you came in late, refer to the start of the presentation. All right, Mr. Johnson.
Good afternoon, sir. How long after submission of the lab, specifically the first lab? Can you hear me?
Yeah, go ahead, man.
How long after the first lab will we get a marked copy so that we can use that to, you know, make sure that our other labs are.
The university standard is that you're required to get back your labs, not your labs, but all assessments within 10 working days. I hope I'm not putting Mr. Sawyers on the spot, but given that I will not be the one doing all the marking, yes, we will try to have a shorter turnaround time, especially for lab 1, so that you understand, how we go about the assessment. But that's a very good question. We will do our best to try and give back lab 1 in as short time as possible. Let me also highlight that, Mr. Sawyers I'll allow him to speak to you regarding the arrangements, the weekly arrangements in terms of the activities. Because you're going to be using software, which you will all have access to, right? Everybody will be able to use the software. You don't have to go into UTech. If you have to go to UTech and use our Power Lab, then we will see how we work that. But everybody should be able to have access. We'll be able to have access. On your timetable, you would also have a schedule for the labs. And Mr. Sawyers will make himself available during those periods to provide some guidance, not to do the labs for you, but to provide some guidance and, help you in terms of navigating and just getting on top of the material as quickly as possible. But he will speak to that in a few. We'll give you some assignments where necessary, and this is just to ensure that you do the work. And students, listen, in the same way that I don't like, I keep saying it, and maybe I need to act on it. But really and truly, I don't like talking, but I teach. Surprise, surprise. I give you work because I need to see or need to determine whether or not you understand what has been done. There is no benefit, absolutely none, to copying. I've had situations where students from the entire group get these fancy grades. Yes? Everybody getting 90s for the assignment. But then when we come to the assessment, they all fall by the wayside. Now, when I see all these fancy grades, I have to make the assumption that, wow, my students are learning. So I move on. So you're not helping yourself. I'm not telling you that you need to go there and fail. That's not what I'm saying. I'm saying you need to ensure that you understand or that you present your work based on your own effort. Yep. Because that's the only way I'm going to be able to determine understanding and know how to, make adjustments or maneuver myself in ensuring that we get on top of this module. I'll give you some reading assignments because, we only have 2 hours per week. I'm expecting you to do the reading. I believe there is a copy of the text. I think I still have it there. It's in Schoology. Please do not download the text, use it online. All right. Counting on your integrity for that one. All right. You present your summaries, then of course, just to make sure that persons have actually done the work. From time to time, I'll just do an impromptu oral assessment. So again, these efforts is to ensure that nobody hides behind anybody. You're in groups, you're presenting work as a group, but I'm going to ensure that people do the work. Because at the end of the day, we want to ensure that, once you have done the work, then, we close your eyes and even without putting in a grade come December, we'll see all P's. That's my objective. That's really my objective, right? So we'll do those assessments. We'll do the in-class assignments, and we'll, present to you the time for submission. Okay. Once we agree on the submission times, I'm not going to change. I'm not going to vary from that. So any assignment, any ad hoc assignment that I give you, which is outside of the schedule that I have already presented to you, once we have agreed on the submission time, then we're locked in on that. The schedule is on Schoology, so you can check that schedule to know what I'll be doing in the next session, and just prepare yourselves accordingly. The mid-semester exam, I do this on a Saturday for two reasons. One, because we're not using the full version of Schoology, the platform is usually unavailable to people like me if there's a high demand outside if there's a high demand within the US, and given what is happening with COVID, yes, we know that a number of students are going back to face-to-face in the States, but there's still a high demand for the Schoology platform. So we use a Saturday where the demand is very low, okay? And we start at 7 p.m. So, persons with religious considerations, I mean, even though the university does not recognize this, but out of respect, we put it at 7 p.m. So it will be between 7 and 9. And please note, unlike networks 1 or 2, this is a one-shot interim assessment for your 20%. Now, if you note, we had indicated that your for the breakdown, the mid-semester is 20, and you had a project, and of course your labs. And then I've been talking about assignments. Don't worry, we'll find a way to include marks from those assignments as part of that breakdown. Uploading, there's no multiple choice here for Power Systems. Everything will be written and uploaded. And as I have done on all occasions, I will provide a test link, and that will be up until the 10th of September. Yes. If you're not familiar with uploading your script, if you want to test some new scanning package, or you bought a new phone and you have not scanned with it before, whatever you need to test in uploading your work, please go ahead. Remember, all material must be uploaded as a single PDF, right? Everything submitted to the Schoology platform must be submitted as a single PDF. Don't submit a series of JPEGs to me. If you do that, when I open it, I am simply going to mark the only JPEG that I am looking at. So I am not going to be going in and out of your JPEGs. So students, please spend the time, use whatever available software is out there. If you are using your computers, fine, scan, create the PDF, upload. If you're using your phones, make sure you can use the scanning packages or whatever methods you are using on your phone. Make sure you can do it and test it. All right. Everything will be managed by Schoology. If you want to reach out to me, the most efficient way is just to send me a message on Schoology. And I usually respond, okay? Just don't send me a message on Schoology with the attachment of an assignment that you missed or you didn't get to upload. I'm not even going to respond. So let me be blunt with that one. I will not even respond to those messages because I think we're being fair in giving you all the opportunities to upload your work, to test, to make sure that you can do it. Yes. And, part of my objective within this module is to help you grow. You're in the final year before you start interfacing in industry in a major way. And so we have to transition from being the young students, to being the persons who are going to be going out there as the junior engineers, the engineer, the trainee engineers, etc., etc. Okay, so this is beyond now just about submitting on time. This is part of your core engineering training of time management and taking responsibility for your action. So I'll just pause here. Any concerns, any questions that you may have?
Sir, in terms of the groups, we choose the person that we want to be in group with?
Absolutely. That is totally up to you. And we will, did I give you a deadline for the groups? I think I did. But if not, we usually give a week. So we're here today. We'll ask that you send those group information to me by Friday. All right. If there are no other.
One more question. The software that we're going to use for lab, is it OS specific?
Again?
The software that we're going to use for our labs, is it OS specific?
Not that I'm aware of. Not that it can work on.
Yes, it is, sir.
It is?
It only works on Windows.
Are you sure about that?
Only works on what?
That's what it says
Windows.
on the website.
That's what it says on the
Microsoft
website?
Windows, no other operating system is supported.
Okay, I wasn't aware of that. But okay. So you got your answer, sir. I thought it was operable on Mac. Anyway, all right. Okay. Let me give Mr. Sawyers an opportunity to just outline any specific requirements that he will have for you. Mr. Sawyers?
Yes, good afternoon, everyone. Yes, thanks, Dr. Isaac, for giving me the opportunity to administer these labs. So just a couple of points I have. For the platform for the lab, I've created a Google Classroom where I intend to host the virtual sessions as well as to distribute any materials I might have that will assist with the labs. I will need the student email for persons who are doing the module. I intend to request that from Ms. Dunkley, but while you guys are here, I'm not sure if you guys have a class rep who would be able to collect the emails of the everyone doing the module and send it to me. I would send invite from Google Classroom. So the first group I have is tomorrow. So I'll be meeting with you guys tomorrow. For the tutorial, I suspect Dr. Isaacs has already uploaded the tutorial on Schoology. I'm not sure if he'll be able to confirm that.
You mean the lab tutorial?
Yes.
Yes, it is already there.
Okay, so when I meet with persons tomorrow, we can, if they have any question regarding the tutorial, we can go through that. And for persons who might have problems with downloading the software, I will also assist with that. So in the coming days, we'll meet and discuss further any issues regarding the lab as we go forward. Any questions regarding what I said just now?
Yes, Mr. Sawyers. Hold on. We're going to do this properly. Ms. Kamok, just raise your hands. I'll acknowledge you. Ms. Kamok?
Good afternoon. Sir, as it relates to the Schoology, I had sent the invite, but I haven't been accepted as yet on Schoology.
Okay, that sounds like you sent it within the last half an hour.
No, sir, I did it yesterday.
Everybody who sent an invite has been accepted. But if you
Well, I
resend
sent it
it,
yet. No, sir,
you
I
can
sent it yesterday because I got the link as it relates to the Zoom link and what we're supposed to do as software, as
All
sheet,
right. Yeah, so
spreadsheet.
I'm giving you the solution. I'm saying to you, everyone who had submitted was accepted. If you were not accepted, just resend the request. But there's nobody in the waiting room right now. Yes, Mr. Cortez. Mr. Wilby.
Yes, sir. I was one of those who sent it since the class had started.
Okay.
And also the virtual lab, will we be using this link for the lab, or is there a separate link?
For that question, as I said, I'm setting up a group Google Classroom. So once I get the emails of all the persons, I'll send you an invite link, and then we'll use Google Meet to host the virtual sessions.
Mr. Sawyers, I saw in the chat, Mr. Johnson says that you will get the names. What I'm going to ask Mr. Johnson to do is just to create a Google Docs with a spreadsheet and post the link for the Google Docs in Schoology. So if you post it in Schoology, it means that everybody, you see, one of the things we want to get away from is, being dependent on any one individual. I want everybody to go to the Google Docs link and insert their information. Then I will pass it on to Mr. Sawyers. All right, Mr. Johnson, so that is what I'm going to ask you to do since you volunteered. Just create the Google Docs with the spreadsheet, post it in Schoology. Everybody will be able to, you can post it in a discussion forum. Everyone will be able to go there, put in their information. And once that is done, we'll pass it on to Mr. Sawyers. All right, remember, he has a class tomorrow.
Yes.
So we'll need this information, by tomorrow morning.
Sorry to be speaking without raising my hand to be acknowledged. I've been looking for the raise hand feature and somehow I can't find it. Yeah, Mr. Sawyers, in terms of our emails, which of them you want? Our personal email or the one that the school has provided for us individually?
Yes, Mr. Freighter, the UTech student email.
Okay, then, thank you.
All right. Okay. Just one last bit of housekeeping. I'm going to ask that you all have your full name displayed. So like 876GB, I have absolutely no idea who you are. And as far as I'm concerned, you're not supposed to be here. So those I don't know, I try to, excuse them. So have your full name displayed. All right, just a little housekeeping. And finally, the official method by which persons should have been engaged in the module is through registration and through the Moodle platform. So I will, after census on September 30, if you are not fully registered for the module, we will be forced to remove you, all right? Just making that clear. All right, thank you, Mr. Sawyers. We will pass the information to you as soon as we get it. We need to get on now.
Dr. Isaac, just one other question, because I know you talk about census date on the 13th of September, but I'm understanding that there has been some bit of problem regarding accounts, IT, and so on and so forth. Why I know this, because I've been to school and I've been trying to get everything sorted out. Now, if it's a case whereas thing is not sorted out by September the 13th, will we
30th, I said. 30.
30th. Okay.
30. So you have 4 or 5 weeks to get it sorted out.
Well, let us hope that there is no blunder on university path. Thank you, sir.
Oops. All right. So let us get into our little power systems. We're going to talk about some basic principles, talk about the fundamentals of your power system. What's a power system, the various parts. Yeah. So what I have here is what obtains for your entire system, okay? And there are three key parts of your system, namely generation, transmission, and distribution. Those are the three primary parts of your system, okay? So we have here generation, and then we have a network which transmits, and then we have distribution. And our focus for this module will be on all three, to different extents. Now, over the years, several things have been happening on the distribution side. And so there's a lot of technology in recent years being applied at that level. Okay, so we talk about smart grid, we talk about smart city, and all of those things that are included. And so we'll spend a little time talking about those niceties, so to speak. But at the generation level, the generators will produce electricity at relatively low voltage as far as a power system is concerned. So we are going anywhere from the region of 13.8 kilovolts. Yes, that's at the generator terminal, up to 24 kilovolts. All right. Now, I'd speak specifically as it relates to Jamaica, where for our purposes, we generate at an average of 13.8 kilovolts. Now, that 13.8 is then transformed by our power transformer to transmission level voltages, or in some jurisdiction, we say sub-transmission. So we take it from the 13.8 and we increase it to, again, in Jamaica, it goes up to 69 kilovolts. And we use that for transmission. But of course, going across island, and let me back up a bit. The purpose of going to higher voltages is that in power systems, our main measure in terms of power is megavolt amperes, the MVA that would have been introduced to in networks. Yes? Now, to reduce losses on your system, what we do is supply at high voltages so that the current that would be in your lines would be smaller. And so your I2R losses will be reduced. So you are reducing losses by transmitting at high voltages. So the reason we are moving it from the 13.8 to 69 is for that purpose. So we have it at 69. Then going across island, we use higher voltages here in Jamaica. So we go up to 138 kilovolts. Right, so 138 is the highest transmission voltage that we use here in Jamaica. In other jurisdictions, we can go as high as 765 kilovolts, right? And that's, of course, when we're going over extremely long distances. To reduce losses on your system, then you go to these high voltages. So we have in terms of voltage levels, we have high voltage, which would be in our case our 69 138, and then we have our extra high voltage, which would be a 765. All right. In some other jurisdictions, for example, in the UK, they operate at 400 kilovolts at the transmission level. Yes. But of course, at those voltages, there are other things that they have put in place, which we will not speak to as far as power systems is concerned. But we leave that when we talk about protection and some of the other attendant issues. So those are the transmission voltages that we operate at. Then, of course, we come to a distribution substation. And in that distribution substation, we come down in Jamaica to 24 kilovolts. Right? Now I know, so most of the substations that you'll see would be your distribution substations. The one that you pass coming up to UTech, that's the Hope distribution substation. Now, here on the island, because we're a small country, sometimes based on what we do in sports, Jamaica may think that it's bigger than what it really is. So in our case, we have both distribution and transmission taking place in the same station. So in Hope, you would have a transmission line that is going from that substation to a place called Cane River. But you'll also have one coming from West King's House. So you'll have a 69 transmission line coming from West King's House to Hope Road, Old Hope Road, or Old Hope substation, we call it. And then that 69 goes to Cane River, okay? But then you have the distribution lines, which are now feeding places like Hope Pastures, coming up to Papine and Garden Town. Those are 24 kilovolt lines. And those are the overhead lines that you'll see on the road. And from those overhead lines, you will have your pole-mounted transformers, which are taking that voltage down to your 415 three-phase, okay? And then, of course, we have our top delta, which gives us our 110, 220, which comes into our homes. However, at the same time, we also have high voltages going directly to some large customers. So a large customer coming from Hope would be our own university. We'd also have a large customer in UWI. The hospital would be another large customer. If we went to another substation such as Rockfort, then you'll have large customers such as the flour mills, the cement company, the airport. I mentioned these large customers because they would be supplied directly with your 24K. And at those facilities, they will have their own substations. So yes, we do have some small substations at UTech which will take this voltage and provide the usable voltages that we require, whether in one of the departments in the School of Engineering or or labs, etc., etc. So generally speaking, that is what the power system is all about. We start from generation, yes? Start from generation. We step it up, transmission, sub-transmission, yes? And then we go to distribution, and from the distribution, we go to large customers with high voltage, yes? And then for other customers, which would be your household, those are then supplied from your pole mounted transformers, giving you your 110, etc. You also have some large customers who would not be supplied by your tap delta, which is the 110, 220, but rather they would get the full 415 3-phase, okay? Because of the type of operations that they have. So some large commercial customers may get the 3-phase, but for, you know, the smaller customers like you and myself, but those who have to pay bills, you'll get your 220 voltage, okay? But of course, in terms of analysis, it would be a bit of a challenge to be analyzing the network looking like this. Yes, it would take some time. So one of the things that is applied is that we use what are known as one-line diagrams. Not everything is shown in this diagram. However, in most instances, what we assume for your generators, remember I said that your generators would be at 13.8 in terms of your terminal voltage, all right? By the way, the limiting factor for your generator would be its ability for cooling. So that is why your generators will be up to 13.8, up to a maximum of 24K, all right? So these being your generators, the general assumption is that it also has the transformers linked to them. So in the previous diagram, I showed you the transformer over here, all right? Generally speaking, you would have these transformers linked directly to your generator. And if you note here, right, this is showing you that it's not really a wire per se, but this is just going onto the transformer bus and taking you out. So in my single line diagram, I may not necessarily show the transformer, but it is assumed that it is there, all right? So we have our generator, or we show our generator. So these would be our generators. Of course, voltages are then raised by our transformer to your transmission voltages. Yes, and they are coming onto what we call a bus bar. So they are coming onto that single bus bar. And by the way, students, this bus bar that we talk about in power systems, if you go back to networks, that's just a node. All right. And you know, so now I suppose as we go through this module, you'll understand why it is that I have opted to teach networks. Because I have to make sure that some things are clear. Right? So at that node, these boxes that you're seeing there, those are just your breakers. But then you're traversing different distances to your substations, okay? So in one instance, you're going over 85 kilometers, 30 kilometers, and these are, you have different distances, obviously. So let's think about it now. So let's say you're at the Huntsville generation plant. You have a Huntsville substation, huge substation. You also have one up by 3 miles. And then you have one by Duane Park. Now, Duane Park is one of our larger transmission substations. So you'll take some 138 kV lines from Duane Park. You have it going down to Kendall. You have one heading out all the way out to Trelawney. Yeah? So that's where you have the 138 kV lines leaving the corporate area. But of course, you then have other generating facilities across the island. Old Harbor, you have out by Huntsville, not Huntsville, Rockford, etc., etc. Right? So you're going to have transmission over different distances. And the distance over which we are going to be supplying this power will dictate just what sort of operation we are going to encounter. So the shorter the line that I'm transmitting over, you know, there are certain things that I won't need to consider. So for this 5 kilometer line, I call that that's a short line. Because it is a short line, I can represent it in a particular way. But then when I come up to my 85 kilometer, this is no longer short. I represent it in another way. But then I go over that and I, you know, go over 100 kilometers, or, you know, we talk about those distances. Again, I'll have to represent it a certain way. But in terms of my one-line diagram, I'm just using lines to connect the different components of my power system. Yes? Yeah. So, any questions so far? All right, good. So this would be what my generating plant looks like. All right. It's not always, when you see what we have at the top there, it's not always, how should I say, carbon monoxide or carbon dioxide, or, you know, NOx or SOx. That could very well just be steam. All right. So these things you're going to encounter in thermal plants. Obviously, my plant here is one of the older ones. You may not necessarily be seeing that type of ugliness anymore, because we move from we have changed the type of fuel that we use to produce electricity. We're going to talk about that in a few minutes. Yes. So this is my generating plant. Right? And it's a thermal plant. Thermal simply means that we're using heat as part of the process of electricity generation. Now, students, important, I'm showing you here a coal-fired power plant. Now, what I want you to always bear in mind is that this coal-fired plant, all the coal is used to do, right? All you're using the coal to do is to boil the water in that. So a coal plant, when we talk about a coal-powered plant, it is simply that we are using coal as the fuel. In this case, it's a fossil fuel, but we are using coal as the heat source for boiling water. And that boiled water, which produces steam, yes, is then used to run a steam turbine. And that steam turbine is used to operate a generator, the same generator that we spoke about earlier. And then that generator produces electricity, which we then increase the magnitude of that voltage, and we go on a transmission system and we send it out to the world. Now, what am I trying to say? If we have a steam generating plant, yes, for a steam generating plant, or our plant run on steam, everything from this point, all of this would remain the same. So we have a steam plant, everything that I've circled there remains the same. However, convention is that we name the plants, the generating plants, based on the fuel that is being used to produce the steam. So a coal plant, all we are saying is that we use coal for boil the water. So think of this as a big kettle, and you put on, you are using coal to boil the water in the kettle. I can also use oil. So an oil plant, I'm using the oil for the fire to boil the water. Or I can pulverize that oil and, you know, use it in a gas plant, right? But the technology here, or the fuel here, gives the name to the plant. So if I tell you about a nuclear plant, right? A nuclear plant, it sounds fancy, but a nuclear plant is still a steam plant. However, nuclear energy is used as the heat source to boil water. We clear on that? Any questions? All right, so our steam plants are all the same. As I said, what I have here remains. All right? The only difference is that the fuel that I'm using to produce the heat to boil the water, what I'm using to boil the kettle. At home, you have options. You can either use coal, wood, you can use gas. Some people may still be using kerosene, but guess what? All of them will produce boiled water for the tea. Yeah? That's it with your steam plants. Of course, you have other generating plants, because remember, I'm coming now to your basic electricity, or is that machines you would have done that in? But anyway, basic electricity is that you produce electricity by the relative motion of a coil and a magnetic field. That is what the generator is. Yes? So your objective in generating electricity is to rotate a magnetic, in our case, and the type of generators that we use, is to rotate the magnetic field cutting across the coil. All right? Now, that is what this is for. So I use a steam turbine, but I can change the means by which I create the rotation. So remember now, initially I said, let me just clear this off. Initially I said for your steam plant, all of this remains the same. Yes? However, for all generating plants, all generators, yes, this is what remains the same. So now, let's come back. Let's come back. If that blue section remains the same, to produce rotation, what are some of the choices I have? If I'm not using steam,
Wind turbine.
I can use wind.
You can use water.
Hydro.
Hydro.
I can use hydro. You finish already?
No, sir. There's another one for it's used in the sea, sir. In the ocean. I'm not sure of the name, but it's basically
Are you talking about OTEC or just the wave motion? Or wave?
the wave motion, sir, but the
All right, so
motion
you have-
itself generates energy.
Okay, so you can use the wave in terms of the oscillation that they produce.
Yes, sir.
Right, with the ebb and flow. But also, if you were talking about OTEC, then OTEC is really taking heat from the ocean. And that OTEC would come back to your steam turbine, because that heat that they would extract from the sea would be used to produce the hot water for your turbine. All right. So apart from those generation systems such as solar, which has no moving parts, that remains. Yes, Mr. Hope.
I was saying, could you just clarify the heat from sea?
No, let's not get bogged down by that. OTEC. Just look up OTEC. Yeah.
No problem, sir.
All right, that is OTEC.
Sir, you can use regular slow speed diesel.
Huh?
Use diesel engine.
Absolutely. I was hoping that someone would come with that. So in other words, you can use your internal combustion engines. So you can use a diesel engine. So when you look on your electricity bill and you see the IPPs, you start thinking, but hold on, how these guys generate electricity? Well, some of them actually use diesel oil, the same diesel oil that you use to put in your pickup. And boy, for those who drive diesel vehicles, I suppose we're now competing with the people who use 90. But anyway, you know, it is not cheap. So you do have slow speed diesel, but of course you also have gasified oil plants. So they produce a gas with the bunker C oil, and that is used to drive the engines. So now that we're talking about liquefied natural gas, LNG, where would LNG fall in all of this? Where would LNG fall in all of this? Huh?
Would it still be the steam?
It could be in the steam.
I'm assuming.
But it can also be a generator.
Okay.
Yes, Mr. Merchant.
Would the LNG wouldn't be it be like an engine, sir?
I'm saying it can be an engine, but it can also be, as Mr. Johnson says, to produce steam.
Okay.
So, for example, the plants at Bogue, all right? The plants at Bogue that use LNG, they originally were set up to use diesel. So when we just started using that combined cycle plant, it was diesel. So what you have are 3 generating units. You have 2 that were being run using diesel. The exhaust of those 2 units, of the 2 engines, the exhaust was then used to produce steam for the 3rd. So that's why we call it a combined cycle, because it is using steam as well as a diesel plant. All right. The 2 that were set up to use diesel were converted to use LNG, which is why the cost for production has fallen. All right. It means, therefore, that we are now running 2 units with LNG. The exhaust then produces hot air, and that hot air is captured and used to produce steam for the 3rd unit. All right. Okay. So in terms of operation, that's what the generating plant looks like, and we'll come back to this, and we'll look at some math, and we'll talk about this in a lot more detail later on in the course. Your transmission system, what can we say? Right? You have your towers. They carry your transmission lines. In some instances, there is redundancy. So what you are seeing here on the left, yes, this would be what the transmission network in the UK looks like. what is so spectacular about this? One, if you look carefully, I don't know whether you can see it, but if you look carefully, there's a little, from what you're seeing, you may just see a little dot on the line. Yes? Now, what that represents, if you note, there are 2 or 3 strands of the line running along here. That's called a bundled conductor. Okay? So they are joined. So the conductors are joined. And so what you have here are the 3 phases. But on the other side, you have the same thing. So in a place like the UK, which has one of the, I mean, in some instances, they say that it is overbuilt transmission network, you have 100% redundancy of their transmission system. So this is 400 kilovolts. This is the same 400 kilovolts. They go into the same substations. So in other words, should one transmission line, for whatever reason, go down, the people in the UK would not even recognize. They wouldn't even know, because the redundancy runs right through the system. Okay? So a few years ago, when they had the blackout in London, it was a major issue because the people of that country don't know what blackouts look like, right? Because of the redundancy. So you have here 2 transmission lines, and we're not going to get into the details in terms of tower configuration, etc., but that's in your text. If you're interested in that, you may want to look at it.
So the redundant one.
Go ahead.
Yeah.
I prefer you raise your hands before you come in. You know, I will take your hand and acknowledge it.
I'm just having a problem with the raise hand feature. I can't seem to
go to where you see the participants, and then you can raise from there. Anyway, go ahead.
Yeah, isn't that an unnecessary cost of one of the transmission line as a redundant?
It's an unnecessary cost. That is what the people of the country are willing to pay for. It's not an unnecessary cost. It is recognizing the importance of not losing power. You see, the more we depend on engineering solutions and technological solutions to our lives, then the importance of having continuous power supply is increased. You think about it, there were several persons who were severely impacted the other day because we had a little tropical storm pass through the place on a wave. Right? Several persons were without electricity after that. You know, we can't operate like that. Yes, Mr. Johnson.
Yes, I was asking if there was a module that would teach us about the transmission lines, for example, the configurations on it.
No, we're not going to get into those details. That's one of the reading assignments that you'll get. All right?
All right, thanks, sir.
Suffice it to say, though, remember I mentioned earlier that some lines, or the lines are of different lengths. And the lengths, yes, will determine how we represent the lines. Now, when you did networks, one of the things we talked about was lump parameter circuits because, you know, we wanted to make the thing nice and easy for you. So when we come now to power systems, we have to think about, you know, we have to we have to make a determination now as to whether or not lump parameter representation is enough. And I'm telling you up front, it's not. But for lines up to 50 miles, 80 kilometers, yes, we call them short lines. These are short. So in a sense, what I'm saying here is that technically speaking, we have no long lines in Jamaica. Right? Or even medium lines to be honest. So, yeah, we might have 1 and 2 just creeping into the medium because there's no 50 kilometers between any two substations, transmission substations. All right. So as I said, yeah, you may have one or two, maybe from Duane to Kendall. That may be a medium line. But anyway, the key here is that for your short lines, yes, we represent them using lumped parameters. So you represent them with R and L, just the resistance and the inductance. Yes, we neglect the capacitance. And remember what capacitance is. Capacitance is that it's based on two charged surfaces separated by an insulator. That's what capacitance is. Yes. So the fact that you have these transmission lines and they are separated by an insulator, in this case it would be air, you would have capacitance. But we are saying if the line is short, yes, if the line is short, then we do not have to consider the capacitance. So your VSD represents your sending end, your VR, your receiving end. All right. For your medium lines, those are between 80 and 240 kilometers. Yes. So that's 50 to 150 miles. Yes. We now represent them using the capacitance lumped at either end of the line. So it will be C over 2 at either end of the line. Yeah. And in your labs, this will be an important component. So Mr. Johnson asked a question if there are any modules I will teach about lines. To some extent, you will have to look at the line structure and bear in mind what information you would be putting into the program, which is why I said earlier that the software isn't about just some computing activities. The software is an actual representation of a power system. I use some familiar names, or we use some familiar names in the labs for you to appreciate that, listen, this is real. But what I have not said to you, but I'm now saying it to you, is that some of the values that we use are the actual values from the power system here on the island. We have made some adjustments, which means that, you know, if you had done the labs before, you still have to redo them, because the values have all changed. Maybe I shouldn't tell you that. Maybe we should just make, anyway, let me leave that alone. But for your medium lines, we represent them with capacitors lumped at either end. So the total capacitance divided by 2, and we put them at either end. So what you have here would be the pi model. All right. So your pi model will be seen here, which of course, going back to networks 2, you are seeing that you have a 2-port network. Good. And this 2-port network, the same ABC, the parameters that we would have spoken about would apply. Okay. For your long lines, lines over 150, this is what you would not have been exposed to in networks. But here we talk about distributed parameters. So in other words, instead of talking about the resistance being X ohms, or the inductance being Y henries, or the inductive reactance being Y ohms, and the admittance, the shunt capacitance being, you know, Z Siemens. What we have with lines beyond 150 would be the resistance per unit length. So we'd have X ohms per kilometer or per meter. You with me? All right. And because they are distributed, what we will discover when we deal with this is that The long lines, we would need to use wave theory. So we'll now need to delve in some of the stuff that you would have covered in magnetics. All right. So we'll look at the wave theory to deal with your long transmission lines. Okay. All right. So this is just showing the representation in terms of your sending and your receiving end for your line. This would, of course, be a short line represented by R plus JX, as we all know it. This is showing the phase relationships. Okay, from your based on the circuit that we have there. But we're not going to delve into these things too much because from a network standpoint, you should have already known this and you would have been able to draw this phasor diagram based on the operation there, which is why it is important that you have those two prerequisites coming into this module. All right. This would be your medium line. So your admittance or your susceptance, yep, you have R plus JX. And then for your long line, you have your distributed parameters, okay? And as I said, we'll come back to this because here you'd have your Z, which is your impedance per unit length, yes? You would have Y, which is your admittance per unit length. And of course, in order to get the admittance, then we'll be looking at an elemental section, which would be your delta X. All right, so over distance delta X, you know, what changes, but we'll get into that later on in the module. We also have to consider, you know, how do we move electricity? How do we transmit electricity? And usually this is where I give the eye opener to our students, because it is at this stage where I say to you that, you know, maybe you had not taken note of the fact that when you go to New Kingston, you see no overhead lines, at least in the heart of New Kingston. You may have one and two on the outskirts. Why? Because we use cables for the distribution of electricity in New Kingston. So New Kingston would be what you would see in a typical city overseas. All right. So the electricity is distributed underground, and so we make the distinction, and that's why this is a lesson on the fundamentals. We make the distinction between a line and a cable. A cable is what we run underground. The line is overhead. All right. So if you think about it, we defined capacitance earlier as having two charged surfaces separated by an insulator. Now, if you look here, these would be the conductors. What you have here, let me just change the color ink. What we have here, that's insulation. Now, for you to have high voltage cables or high voltage conductors in such close proximity and not have a short circuit means that the insulation would be of extremely high quality. So in other words, going back to your machines, what this is saying is that the permittivity or the relative permittivity of this insulation will be very high. With high relative permittivity, then it means that the capacitance would also be high. So what can we say about the cable relative to the line? For your cable, your capacitance is high relative to the inductance. For the line, it's the reverse. So you have higher inductance relative to capacitance. But if we compare capacitance and capacitance for the line and the cable, for the cable, it is much higher than for the line. Again, because for the cable, we have the charged surfaces in close proximity, yes, separated by super insulators. Everybody with me with that? All righty.
Yes, sir.
So
Yes, sir.
So here we have, typical transformer, your power transformer. Unfortunately, we locked in our rooms. So we won't be able to visit a substation. Even though I am really hoping that for those who will do protection, by then we will be able to go into the field, so we'll visit a substation, visit a generating plant as part of that module. But anyway, for now, this is the best I can do in terms of getting up close to a power transformer. Okay? All right, we have discussed this already. I don't need to go back to that. So, students, you remember that's my one-line diagram. But you would agree with me that we're going to have a challenge doing any sort of calculations, and there'll be no point you coming into power systems and this man telling that you have to know, you have to pass networks 1 and 2. And then you come into power systems and we do no calculations. That would be rather boring. So in order to do the calculations, what we have done is to convert this one-line diagram into what we call a nice single-line diagram, which shows the reactances of the lines and the transformers. And we have the reactance of the generator. Yeah, we have reactance and resistance. We have generation and resistance. And what does this look like? This looks like what you have recently put behind you and thought you will never see again. All right? Looks like a nice network. So we come back to circuits and networks. All right? Or networks, 1 or 2, whichever one you prefer. So we come straight back there, where I now have 2 generators. I have some reactances, and I have to be able to determine, what current is flowing where, because, whether we like it or not, we will have to do some calculations. We'll have to know what current is passing through this line. We need to know which direction it is flowing, how much current is leaving our generating unit, whether or not current is leaving there and coming into this, all of that. So how do we do that? Here is a challenge. Here is a challenge, students. You remember what we said about the power coming from the generator? It's a freighter. What comes immediately after the generator? It's a freighter.
Yes, sir.
Immediately after the generator, what do we have connected?
The transformer, sir.
The transformer, all right? And in your own words, what's a transformer? What's a transformer? I know it is something that, we'll accept that we all know, but nobody has ever really asked you to define what a transformer is, eh? What's a transformer?
Well, a transformer, sir, is a device that is used to step up or step down the voltage.
All right. Okay. But in power systems, yeah, we know that is its operation, but really it's a device used to connect systems of different voltages. That's what it really is. The transformer is the only device that can do that. Connects parts of your network of different voltages. Therefore, what can you say if this is my generator? And remember I said that it is assumed that behind the generator we're going to end up with a transformer, no? Because the generator voltage would not be interfacing directly with the system. This also, that 220 kilovolts, Ms. Grant, Ms. Gray rather, what would that 220 volt represent? What do you think would be represented here? Ms. Gray?
So the transformer.
220 volts? All right, fair enough.
Sir, missed the last half an hour after class, sir, please.
Oh, okay, okay. Missing
Just join.
any part of this class can be rather painful. But Mr. Boss, you have been here all along. What would the 220 and the 110, what part of the network would those represent? Look at the voltage. What would it represent? Mr. Bosso, Taran?
Yes, sir.
What would that represent? What would represent at those sections?
So those are the voltages coming from the transformers.
All right, that's Mr. Merchant, you were saying? What would represent at those points?
Sure, because of the...
No, man, don't give me no explanation. Just tell me what would represent it.
A line?
The line, absolutely. The transmission lines.
Yeah.
Right. Because you would have, you are now at 220 kilovolts. It's not at a point, you know, it's this whole section I'm talking about. All right, so those would be a lines. So what do we have here, students? We would have a mixture. We would have let me not use a mixture. We would have a combination generator voltage, transformer, line, transformer, generator, and of course the same would be represented down here. So, agreed? But watch me now. When you're in networks, one of the things you could rely on is that the same current would flow from this point over to this point. And the same current will flow from here to here. When power systems are not so it go. Because in terms of the rating of a transformer, in terms of how we rate a transformer, maybe I should ask, who else I can call on now? So Science, what you still doing here, man? You want to hear this again?
No. Yes, Doc, I'm taking in information now. It's never too much to learn more.
All right, so Mr. Duncan, talk to me now.
Yes, sir.
In terms of the rating of a transformer, how we rate transformers?
In terms of their the maximum, well, the input and the output voltages, the currents.
Right. So this is something new for you then. So we actually rate transformers by their MVA rating. So it's their power carrying capacity that we use to rate them. So we rate them based on MVA. Don't go nowhere, Mr. Duncan. We're not finished with it yet. But the transformer has different voltages on either side, on the primary or the secondary. You agree with that?
Yes, sir.
All right. So if you have different voltages, what would that say to you about the currents on either side?
Well, sir, the currents would change, but the ratio.
Don't give me no but, man. Just tell me. What would you say about the current in the primary or the secondary? Wouldn't they be different?
Yes, sir.
Good. So the actual current, students, thank you, Mr. Duncan. So the actual currents on either side of the transformer will be different. However, I'm sure that I have jarred your logic by suggesting that the same current would not pass from bus 1 to bus 2. But I am right. But I am also wrong. Let me explain. The current on either side of your transformer will be different. However, there is a current that will remain the same from 1 to 2. And that current is known as the per unit current. So we'll talk about per unit current. Per unit current comes into play when we have transformers in our networks, because the per unit current on the primary side of your transformer will be equal to the per unit current on the secondary side of your transformer. And that is what I want to introduce you to this afternoon, and then we will wrap up. All right? I am a little behind in terms of my delivery, but we'll catch up in the next class. So per unit is what I want to introduce you to, okay? The per unit system. The main purpose, students, in using per unit is that it simplifies equivalent circuit of our transformers. So that is just the fancy way to say it. What am I talking about? It simply means that the ideal winding of your transformer can be eliminated, and I put that in quotes, and that will ensure that the voltages, currents, and external impedances or admittances do not change when referred from one side of the transformer to the next. All right? Now, what do I mean by that? Everybody here would have completed machines too, right?
No, sir.
No, sir. That's a
It's an elective.
No, sir.
What do you mean, no?
It's being offered right now. It's a 4-year module, 4-year elective.
That's an elective.
It's an elective?
It's a 4-year elective.
I look like I need to. Anyway, we'll leave that one.
Yes, sir. Find something else.
Yeah, we're going to leave that one then. But all right. I don't know how to proceed now. Anyway.
So machine one is not sufficient, Mr. Isaac, Dr. Isaac?
So from your machines, and I suppose you may have done, when we are, or let's not even talk about machines. Let's talk about, well, you would have done something similar in electronics, electronic devices. I'm sure that one compulsory. So when you were doing amplifier circuits, and you were connecting 2 stages of your amplifier, or you're doing impedance matching for your amplifiers, yes? You could use direct coupling. What the other one? You can use transformer coupling. That's right, no?
Yes, and capacitive.
You're causing me to dig into some things I did 20 or 30 years ago, and it's kind of hard. But anyway, so you can do direct, you can use capacitor, you can use transformer, no? When you were using the transformer, yes, you remember you had to multiply by the square of the turns ratio? You remember that? Well, nobody remember. But this is serious. I need to talk to Mr. Top, because I know same teacher. No?
Yes, sir. That was done in machines 1 as well.
It was done in machines 1. Oh, beautiful.
Yes,
I will give Mr. D the extra bullet for that. So, you in referring an impedance, looking at an impedance across a transformer, you would square the turns ratio. But in power systems, if you were to do that, I guarantee you that you wouldn't complete one problem. So what we do is to use the per unit representation. And so the per unit impedance of your transformer will be the same whether you're looking at it from the primary or the secondary side. Okay? So the per unit value would remain the same whether you are going from secondary or primary. And that is the beauty of this system, because it simplifies the transformer and it gives it a simple per unit reactance value. And then if you had that per unit reactance value, you would then have this as a simple series parallel network. Well, not series parallel because you have two sources, but you'll have it as a simple network that you could use your standard networks analysis tools to solve. All right. Yes, Mr. Ho.
So, sir, so if we have our per unit, so we will no longer look at the current on either side of the transformer then?
What you would have is the per unit current that will flow. However, it does not mean that the current on either side would be the same. I said that at the beginning. The currents would be different, but the per unit current would be the same, right across.
Same, yeah. Okay.
All right. So some other benefits of per unit. With practice, when you buy a transformer or when you doing work with a transformer, the per unit value for certain types of transformer remains the same or is within a very narrow range. Yes? So you are able to quickly check for errors. So if I were to be designing a network or somebody design a network for me and give me the data sheet and I see a per unit value of 0.9 for the transformer, I know it's foolishness, because that is way outside of what the per unit for a transformer would be. I see a per unit of 0.85 for a generator. I know there's something wrong with that. So in other words, with practice, yes, with experience, you will know and have a feel for the narrow ranges in terms of the per unit values for particular pieces of equipment. For those who are already industry, the manufacturers will specify their ratings in per unit. And this would be the per unit in most instances on rating. And we'll explain that in a few. So I tell you what per unit is used for. What I now need to do is to tell you how to calculate per unit. We have only 5 minutes left. Well, really and truly, I should finish here, but let me just give you the basic introduction and then we can take it from here. All right. So per unit, a per unit value of a quantity is the actual divided by what we call a base value of the quantity. So your per unit quantity is the actual divided by the base. So we have per unit voltage. It will be the actual voltage divided by the base voltage. Per unit power, actual divided by base, and so forth and so on. Nothing fancy. So your per unit, actual divided by base. But this is important that we define what we're talking about base. What is this V base, S base, I base, and Z base? All right. We finish with this? I'm assuming you guys taking notes, And by the way, I spoke to 876 GB already, and it is still there. If I see 876 GB next week, then I'm just going to remove you from the room without even alerting you. All right? And that goes for everybody who do not have their proper names displayed. All right. So this is how we define per unit. Let's talk about the quantities now. The actual quantity, yes, is the value of the quantity in actual units, meaning volts, amperes, volt amperes, yes? And the base quantity also have the same units, which means that your per unit is dimensionless. Now, folks, and this is why I'm going to end just by this brief introduction. Two base values. Yes. The three phase, line to line, or the phase value, line to neutral, voltage, and the three phase or single phase apparent power are arbitrarily selected. You remember when we used to talk about selecting your reference point? When we were doing nodal analysis, it was totally up to you. Same thing applies for per unit. It is one, you know, let me put it in, let me circle it in red. It is 100% your choice. It is they are arbitrarily selected. All right. Finish with that. Okay. So the two values that you select will be V base, S base. V base in kilovolts, S base in megavolt amperes. All right. But of course, just like the reference point, there's some common sense to all of this. So usually we take V base to be the base, the voltage of one of your transformers, and the S base we take it to be a number that is easy, you know, easily divisible. So we normally take like 100 or 50 or 10, you know, one of them numbers. But it's up to you. It's totally up to you. Right? And the units that we use here are based on typical system because in your power system, we're talking about kilovolts. That's the standard volts, voltage level that you're going to be using in your power system. Right? And for your power, we're talking about MVA, megavolt amperes. So we're not talking about kVA. We're not talking about VA, MVA. Right? But bear in mind that although we choose this, it's really the volt amperes and volts that we're using. Okay? So, you know what? It is now 3 minutes to 5. I'm going to pause here. Just whetting your appetite a little. All right. Yeah, we leave it here until we meet again. It means that I have not accomplished my objective today because we should have completed per unit. But it is best if we take it slowly. All right. So you can review what we talked about today. Make sure you have an appreciation for it. The material that's in Schoology, spend some time, look at it. Make sure you are comfortable with what we have presented. And then when we come back, when we meet again next week, we're going to pick up the pace a bit, right? So you can check your textbook, you know, have a look at per unit, and we will take it from there. Yes, Mr. Wilby.
Sir, there's a matter I would like to speak to you about after, sir.
Yeah, sure. What am I doing? Just a minute. Don't nobody leave yet. I need to take the register. Just a minute. Okay, all right. I'll finish that up tomorrow. Okay, students, take care. You may now leave. Have a good evening. Yes, evening has started.
Okay,
So have a
sir.
good one. Take care.
Okay,
Okay, sir, you too.
Sir Isaacs. Dr. Isaacs. One question here. In regards to the textbook, I'm looking in Schoology, but I don't see it.
You open the
Yes,
the
there's a
syllabus?
module.
You open the syllabus? The syllabus is there.
Let me go through again.
Huh?
Yes, I am going through the syllabus. Content. Units. Okay, all right. Okay, sir, thank you.
All right.
So in terms of the persons that we will get into group with regarding the labs, what we should do, message on Schoology with the group, the name of the person?
Can include that in the document that Mr. Johnson will provide. All right.
Okay, sir.